guys, please make sure that your Zoom name is the same as the name on Canvas, so it's convenient for our TA to put a grade for you for the attendance. And also, if you want to get the bonus attendance for this class attendance, please make sure that your video is on, so we know that you're actually taking class or you are not like doing something else while just logging. So in the last class, we talked about the stress on the oblique plane. So this is for the application. What if there is a joint on the oblique plane, which means that, well, it could be on a plane that is perpendicular to the x direction, but it could be in any random direction. And also for this welded joint, you can, as a structure, you need to check if it fail on the cross section, which is the content we learned in the first section. You also need to check if it will fail on this welded joint, which is a inclined plane. It's not necessarily perpendicular to the actual direction. So in this situation, we do need to find what is the stress, normal stress and shear stress on the inclined plane. So to solve the problem, of course, we need to calculate the normal stress, shear stress, we need to find out what normal force and what cross-section area. So in the end, it's about the normal force over the area of the normal force applied and shear force and the area of the shear force applied. So let's say if we define the theta is the angle between the actual direction of the structure and the normal direction of the plane. Be very clear, our definition of theta here is between the actual direction of a structure and normal direction of a plane. How we define the plane direction is the normal vector of that plane. It's the consideration of the plane direction, right? That's why when we say positive x plane is a plane that is normal vector positive in the positive x direction. Negative x plane means it's a plane with the normal vector in the negative x direction. Same thing, this is the normal vector of the plane. So the angle theta is defined in this way, and all our derivation are based on this definition. You will see that in solving a lot of problems, they give you angle, this angle, that angle, not necessarily always defined in a way that is the angle between the actual direction and the normal vector plane direction. So then you need to convert. And also you need to know that all our derivation are based on this definition. Of course, you can define your own theta and you can have your own set of equations. So my point is that if you want to use the equation here, you need to follow this sign. What is this theta defined? So for the normal force, of course, is we can find this this component. So it's equal to P cosine theta based on our theta definition, and the shear force is sine theta, P sine theta. And for the area, if we have the cross-section area is defined as A naught, then the A theta is equal to, well, A theta times cosine theta equal to A naught cross-section area. So now here we have, this is A theta, this is A theta. This is the equation of finding the normal stress and the shear stress on this inclined plane. And of course, to decide back to this real world application, to decide if this joint will fail or not, we need to compare what is the actual stress, normal stress on this plane, and what is allowable normal stress of this, let's say if it is glue joint, and what is the actual shear stress on this inclined plane, and what is the allowable shear stress on the inclined plane, to see if it's safe or not. Only unmute if you have a question to ask, otherwise please mute the microphone. So now let's check several special situation of this stress on different angle of the plane. The first one, of course, if we consider theta equal to 0, which is in the cross section. So when the theta equal to 0, it means that it is on this cross section. So what is normal stress and shear stress? And we can check if it makes sense. So when theta equal to 0 degree, cosine theta equal to 1. So this one is equal to 1. And so this normal stress equal to P over A naught, which is consistent with what we learned in the first section, right? We talked about that, okay, on this cross section, if you have the tensile force P applied, and you have the cross section area A naught, so the normal stress should be equal to P over A naught. And for the shear stress, use the second equation, sine theta equal to 0. So shear stress on the cross section should be 0, which makes sense because on the cross section, when you only have tensile force applied, there should be no shear stress on that cross section. Let's now rotate theta equal to 45 degree. Now cosine theta 1 over square root 2, so square it's 1 over 2, so becomes a half 2 A naught. And now 1 over square root 2, 1 over square root 2, so it's 1/2. So basically mean that when you rotating this plane, and when this is 45 degree, let's assume this is 45 degree, then on this inclined plane, the normal stress becomes P over 2 A naught, and shear stress is also P over 2 A naught. And now let's keep rotating. What if we have a plane that is in the axial direction? Let's see what is the normal stress and shear stress. So in that situation, theta should be equal to 90 degree. Then of course, cosine theta equal to 0, sine theta, and the second equation, this one equal to 0, so it's also 0. So basically it means that when you have tensile force applied on the plane that is in the axial direction, just no normal stress, just no shear stress. So now why we do this? Because a lot of times we want to understand why certain things happen in that way. So let's say probably some of you have seen this kind of tensile test before. This is the simplest test for mechanics materials. So let's assume this is a tension test. The tension test basically means that, let's say you have a 1D bar structure and apply tensile force, and it will break. And for different material, it will break in different ways. So let's assume that these two pictures, one is brittle material, one is ductile material. Which one is brittle? Which one is ductile?
The top one is brittle and the bottom one is more ductile.
Yes, thank you. So for a tensile test, this one should be the brittle material, and this one should be the ductile material. Can you explain why?
It has to do with the cracking on the top one. It's more uniform, and so it looks like it broke cleanly. And the bottom one, the material was stretched before it finally broke.
When you do a tensile test, it can fail even without a crack. It does not relate to the crack. Yes, a lot of failure is because of crack. We talk about the fatigue problem in the more advanced structure class, but here let's say in our mechanics material, we assume that the structure is perfect. There's no crack. It's purely failed because of material itself. So any other idea why brittle material fail in this way?
One has no backing and the other one has backing.
Sorry, could you please explain? The sound is breaking, so I didn't really understand.
The brittle one has like no necking, and then the ductile one has necking, so it like shrinks before it fails.
So you said brittle one has what? Sorry, I didn't get that word.
Like necking, like the brittle one
Oh,
doesn't
necking.
have any.
Okay, necking. Okay, so I guess you guys learned a little bit from the maybe this is some materials class before this one. So yes, for ductile material, if you remember, there's like a stress strain curve, and for ductile material, there's some necking, and then you do a break. But bridge material, well, it fell directly, right? Yes. So that is also that is one part of explanation. And for more closely related to what we are talking about here is that you can see the bridge material, it fell on a plane that is perpendicular to the axial direction, which means that it fell because of this normal stress. And for ductile material, it fell on a plane that is 45 degrees to the axial direction. It fell because of this. So for the first one, brittle material, it fell because of normal stress on the cross section. And the ductile material, it fell because of a shear stress on a 45-degree plane. So let me explain. So for the brittle material, I guess you guys learned the material science before. So basically, brittle material fell because of the break in the atom, the bond between the atoms. So it fell because of normal stress, right? So among the normal stress, you need to figure out on which plane it has the maximum normal stress when you rotate the plane. And comparing these three things, of course, you can have a function plotted in MATLAB. So 0, 10, 30, 45, 50, 80, 90, and then you have a curve. And you will see that when you're rotating the plane, the maximum stress of normal stress is happen at when theta equal to 0, which means that the maximum normal stress it happened when it's here. The area, the plane is perpendicular to the axial direction. That's why for that brittle material, it fell like this. This plane is perpendicular to the axial direction. Now for the ductile material, again, back from your background in material science, the ductile material, it does not fail because it's breaking the bond. It's not fail because of normal stress. It fail because the sliding of the atoms. So for the sliding of atom, it's related to the shear stress. So for the shear stress, now you check this row. And you can also do a plot like from 0 to 10 to 20 to 30 to 45 to 60 and to 90. And you will see that maximum shear stress happens when theta equal to 45 degrees. This is where the maximum shear stress occurs. And then maximum shear stress when this theta equal to 45 degrees. That's why for ductile material, when it fell because of shear stress, it fell on this plane, 45 degrees. Does this make sense or not? Okay, any question? Okay, so this is the stress on the inclined plane. It's not only for us to solve for this situation, like for different joint, how we can determine if it fail or not based on comparing the actual normal stress, shear stress on the inclined plane and the allowable normal stress and shear stress on that inclined plane. We can also use to explain why for the same tension test, different type of material fail on different plane. I hope this makes sense. So now let's do a example problem. We have a glue joint. So this inclined plane is a glue joint. We have tensile force applied at two ends. Allowable normal stress of the glue joint is 700 kilopascal, and this is allowable shear stress on the inclined plane. And we assume that, of course, if it's a real world problem, you need to check if it will fail on this glue joint. You also need to check if it will fail in the material itself, right? But this for this example problem, let's only focus on this glue joint. We assume that strength of joint control the design. It will not fail in the structure itself. It will only fail, if it fail, it only fail on this glue joint. So we need to decide if this structure is safe or not, or what is largest P can be applied to make sure that the structure will not fail on this glue joint. how to solve this problem. Anyone?
Would you just write the equations for shear normal stress and then derive the P?
Yes, thank you. So basically, we need to find what is the actual stress, actual normal stress on this inclined plane and compare it with the allowable normal stress, right? And of course, the actual normal stress on this inclined plane should be a function of P. And we also need to compare what is the actual shear stress in the structure. It should be a function of P, and then we compare with allowable shear stress. And then we can solve for what is the largest P can be applied. So let's do it one by one. Let's first check the normal stress first. So the actual normal stress in the structure should be the equation we just derived. P anal cosine theta square. P is something we need to solve. Cross-section area, the dimension, cross-section dimension, they're given 70, 50 millimeter. Let's use Newton and meter. Cosine, what theta should we use here? Is it cosine 40? 50, thank you. So this is equal, this should be smaller or equal to allowable normal stress. Oh no, Pascal. Again, convert everything to Newton meter. So the force you solve should be Newton. Where is the 50 degree from? So why the 50 degree? So that's why when in the conceptual part, I keep explaining that why do we need to be careful? We're very careful about the definition of theta. In the definition of theta, in our derivation, it is between the angle from the x direction and the plane direction. So it's this theta, and of course, this theta is also equal to this theta, right? Because if you draw let's say this is the y direction, and these two angles should be the same. So now, let's say we already know that if you want to use the equation we derived in class, this is a theta. This is 40. What is the theta? We should use 50. Right? Does this make sense or not? Okay, great. So well, you can either consider it's a plane with a vertical direction, transverse direction, or I think most textbook the statement is the x direction and normal vector plane direction, well, both of the same. So you understand in whatever way you prefer. And of course, you can define your own theta and derive your own equation. So now for the shear stress, oh wait, I didn't calculate that one. Yeah. So now P I calculated here is 5930 Newton. So I got a question in the office last time. So asking about, so let's say the actual stress should be lower or equal to the allowable stress. Should we use smaller or equals and smaller, or use equal? It doesn't matter. In your homework, in your quiz, in your exam, we just want to find a threshold value, right? So you can say that this P should be smaller or equal to this value. You can say P is smaller than this value, or you can say P equal to this value. We will not give penalty because I like insist a certain way and the other two way they are wrong. No, it doesn't matter. So if you really prefer to put in this way, that's fine. Or you just want to put in this way, or just put it as equal, that's all fine. There's no penalty for that. P A naught sine theta cosine theta. And again, theta equal to 50. And this should be equal to the threshold value, which is 560 Pascal. 10 to the third Pascal. So P equal to 3980 Newton. What is the maximum P can be applied? See, it's equal. What is the maximum P can be applied? Yes, thank you. Thank you. So again, as I emphasized in last class, a lot of time in the test, in the quiz and exam, some students get panic and they couldn't think very clearly. So whenever they say, okay, a largest force can be applied, so they choose a larger one. But here, if you put some understanding there, it should be, if you apply this force, it can survive both this stress. If you apply this force, it means that, okay, it can survive from normal stress, but it fail at shear stress. So when you choose the force, that makes you safe for both. Sorry, 7. Yeah, 7, sorry. Any other question?
Can you explain one more time why it's 50 degrees?
So our definition of the theta is, let's use a different color. This is the theta, right? This is theta. Or if you understand in the way that, as I said in the class, in the textbook, they put it as the x direction and the normal to the plane direction. So this is theta, it's the same thing. So let's say this is normal to the plane direction. This is the x direction. This is a theta. So now you have wait, let's not make it too complicated. You have this angle equal to 40, it means that this angle equal to 40. If you have this angle equal to 40, it means that this angle equal to 40. So now this is perpendicular, so this one should be 50. Make sense or not? Our definition of theta is the angle between the actual direction of the structure and the plane normal and the vector normal to the plane direction. So this is the how we derive our equation. So if you want to use the equation, you need to follow this definition of the theta. So now you have this one equal to 40, it means that this one equal to 40, right? This angle equal to 40. So the angle between the x direction of the structure and the vector normal to the plane direction, this one becomes 50. Okay, any other question?
Question, can you explain one more time why we picked the smaller value?
Yes, so we calculate two values. So basically it means that when we have this value, this structure is safe for normal stress. It will not fail because of normal stress. When we have this much applied force applied, it will not fail because of shear stress, right? So now we want structure to be safe. You mean that it should safe for both shear stress and the normal stress. If we chose this one, this 5930, it means that
Mhm.
okay, it's safe for normal stress, but it will fail because of shear stress,
Oh, I see, I see.
right? You need to choose a stress, then make sure that it's safe for both.
Okay, that makes sense.
Yeah, which should be the lower value, not the larger value.
Even if you pick the lower value, it won't break under. Okay, that makes sense. Thank
Yeah.
you.
You're welcome. Any other question? And similarly, I can change this problem. Let's say I have the force applied given. I give you some value. Let's say I give you 4,000, and it becomes design problem. I don't know what the dimension of this one. And the same thing, I give you the allowable stress, allowable normal stress, allowable shear stress, and you need to calculate what is the minimum width. Let's say this is the width of the structure of this bar, 1D bar. Then you will have two values. So based on the normal stress, you calculate one. Let's say this is a B, B1 because of normal stress, and I have a B2. And the question is, of course, what's the minimum B dimension? And out of the two, you need to choose the larger one because if you use the smaller one, it's safe for one stress and fail because of another stress. But if you choose a larger one, it can survive for both. So even though the problem statement asks you what is the minimum dimension of B, you need to choose the larger one to survive for both stress. Make sense or not? Okay, any other question? If no question, I guess you guys are fine with this one. Let's move on to a new topic, safety factor. So this is a typical tensile test, as you can see. It's moving, right? Yes, it's moving. This is metal, of course. Metal is ductile material. Normally we would say that the glass, ceramic, those kind of material, they are ductile material. They're brittle material. So the metal, they are the ductile material. So it fell under 45 degree. So the next topic is the safety factor. It's a cross section. Why the area for each of them was the same? Go back to the definition of A naught. What is A naught here? A naught is the cross-section area, right? Did I answer your question? A naught is the cross-section area. That's why the area for each of them is the same.
I had one more question about clarifying. You said that if the question had asked for the minimum axial load, that we choose the largest answer. Can you explain, like conceptually why that is? Yeah. You said hypothetically, if it was asking for the minimum axial load, you would choose.
Dimension. Are you talking about the dimension? Like, what's the minimum dimension of that part I just explained?
Oh, was it? Oh, it was the dimension that you were talking about.
Yes, I said this one specifically is asking about what's largest axial load to be applied to make sure that structure is safe. We need to choose a smaller one to make sure that it survives for both sigma and tau. But I could change this problem to I give the force applied. I give the allowable normal stress and shear stress. I ask you what is the minimum dimension here. Let's assume that it's the width B. I ask you what the minimum dimension B here, then you need to choose the larger one to survive for both. That's what I said.
Got it. Thank you.
You're welcome. Now let's back to the safety factor. So why do we need a safety factor? Because if you consider like we say yield strength, arming strength, we do these tensile tests for different kinds of material in the lab, and we can have a what is yield strength, which is the starting of the material when it has plastic deformation, right? It has linear change and then it has plastic deformation. At the starting point of plastic deformation, or sometimes test we use the 2% of offset, it's almost the starting point of the plastic deformation. We consider that stress is the yield strength. And the strength, the stress that cause the actual break of the material is the strength that, well, because the necking is the stress that's lower than ultimate strength, and before the breaking, the maximum stress generated in the structure is the ultimate strength. So these are the data we get from the lab when we have a specimen and then when we do the test. But a lot of times, let's say if you have different batch of the material, let's say all of you have the aluminum 6061, but it's different batch material. You cannot guarantee that the aluminum strength, yield strength, they are exactly the same, because the process of how this material is made may be a slightly different. Sometimes maybe it's like heat treatment procedure, the temperature speed, the speed of temperature increase and the temperature decrease, they are not exact same. So there's some uncertainty of the material itself. And also when we say that, okay, let's design a bridge and we have assumed maximum stress caused by the different car drive on the bridge. But what if in one day there's a huge truck with very heavy load drive through? There's some uncertainty of the force applied in your structure also. So to accommodate those uncertainty, we normally put a safety factor, which means there's some margin. So even though there might be some, my batch material is much weaker than what is supposed to be tested here in the lab, or the force applied is much larger than what we assume to be in the structure, then this margin can make sure that, okay, my structure is still safe. So, or safety factor. So safety margin is the difference between the two values. Safety margin is the ratio between two values. So both of them are fine. We are talking safety factor here. So let's say if we have the yield strength of the material is 100 megapascal. If we want to design a structure that has safety factor 2, it basically means that the maximum stress in the structure should not be over 50 megapascal, right? So this means that safety factor is equal to 2. It's a ratio between these two. If we define when the material starts to yield, it's considered as a failure of the structure, and we want a safety factor 2, then we need to make sure that the maximum stress in the structure based on the calculation should not be higher than 50 megapascal. So we can say the safety margin here is equal to 50, which is basically 100 minus 50, or you can say safety factor, which is this ratio equal to sigma y over sigma s equal to 2. So this is the safety factor. And we can do safety factor for both normal stress and shear stress. So if for normal stress, basically is the yield strength over maximum normal stress. If we calculate based on the shear stress, safety factor can also equal to, well, if the material fail because of shear stress, then allowable shear stress or yield shear stress, maximum shear stress in the structure. So we can define a safety factor in either way, determined by how your material will actually fail. If it fail because of normal stress, you can use this one. If it fail because of shear stress, you can use this one. And of course, this is in the lab how we do the test of the shear. So this is the single shear, which means that the shear force is carried by one area here, double shear carried by two area. So this is definitional safety factor. I want to emphasize here that safety factor should always be calculated based on the stress. And this stress I put as yield strength here because we consider that when yield strength, the starting point of yield strength is the starting point of plastic formation, and we most of the time we consider that when there's plastic formation, you consider failure, because let's say if you have a aircraft, you don't want like during every flight, just some plastic deformation accumulated, and your airplane, the fuselage, getting bigger and bigger because of plastic formation. Because plastic formation cannot be really, when the stress released, it cannot go back to zero.
And after the yield point, the material is being plastically deformed, right? So it can't go back to
Yes.
the way it was before.
Yes. So I think what you guys learned in the previous class is a curve like this. So let's say this is a strain, deformation, this is a stress. So first you have a elastic range. So the deformation and the stress is linear range. So we can say that this is the proportional limit, right? And then 2% offset, plastic deformation, consider as yield strength, and then Archimedes strength and breaking. I'm really horrible at drawing this. So let's say this is the point where to break. And this is a maximum sigma Archimedes strength. My cat is here. And let's say this is a yield strength. This is a proportional limit. So before the proportional limit, there's some deformation, of course, but it's elastic. Basically mean that, okay, you apply force, it will have deformation. When you force go back to zero, deformation go back to zero. This is the plastic deformation. But once your plastic deformation start, you apply force, the stress increase, and when you unroll the structure, the force back to zero, the deformation does not go back to zero. So the part that the plastic deformation will stay. So basically mean that, let's say during every flight, if you have the pressure, let's use aircraft because many of you are from the aerospace program. Let's use aircraft as fuselage as example. Let's say for the fuselage skin, during the flight, there's internal pressure to make sure the passenger can feel the pressure same as sea level, but outside pressure is almost zero. So the pressure difference between the inside and outside of the fuselage skin. And this pressure difference will generate stress on the fuselage structure. And after flight, when your aircraft go back to the ground, the inside outside pressure, both of them, they are sea level. So this pressure difference becomes zero and the stress will go back to zero. So basically mean that, okay, during flight, it stretch, stress increase, strain increase, back to the ground, back to zero, stress back to zero, strain back to zero. And if everything is in the linear range, it's not elastic deformation, everything should be fine. But let's say if our stress goes beyond your strength, there's some plastic deformation and your aircraft back to the ground. Plastic deformation remains. And next flight, you go again and you come back. So this accumulation of deformation, it basically means that your fuselage will get bigger and bigger. So that's why a lot of times we consider that yield strength is the failure of structure. But it's not 100%, of course. Let's say if you make a table for yourself, you probably don't mind about plastic dimension of table. You probably just concerned about when it's actually break, right? So it's not always the situation, but most of the time we consider yield strength. So in some textbooks, they use loss of function strength. of the maximum strength. That is more accurate definition, but I think in our class, this should be enough because a lot of time we just have the yield strength. So this is the safety factor definition. It should be in terms of stress. It should not be in terms of the force because stress and force are not always in linear relation. Let's check the for variable safety factor. Ultimate strength. Sorry, I should write this clear. This is the ultimate strength, UT. This is the yield strength. This is the proportional limit. Proportional limit, yield strength, ultimate strength, break. This one is not important. This is a topic in mechanics, in material science. So the key thing here, I want to explain why we use yield strength here. And the thing also I want to say is we should always define safety factor in terms of stress, not in terms of force. So I try my best to make my lecture consistent with textbook most of the time. As I said, for example, the shear stress sign convention, maybe different textbook, different convention, but I think that is fine because, well, it's sign convention. So I made my best to be consistent with textbook. But here, I want to say that when you read textbook, you may see some inconsistency. I can show you here. This is okay, this is stress. So for the safety factor, it said that, okay, the first definition is defined based on the force applied, the ultimate force applied, load applied, and allowable load. And then they say if a alternative definition of safety factor is based on stress. So in this test, we consider both of them are okay. And this is a different textbook, mechanics material, both of these are mechanics. And so the first define is because of force of fail and force allowable force applied. And say if this force applied is in a linear relation to the stress, then we can have this one. So to define based on the force first, and then if they have assumption, the linear relation between the force and the stress, then we have these two. So this is the second version of mechanics materials. And some of you may took the Mach 1. Mach 1 is the cat is here. So this is a Shigley's textbook, the mechanical engineering design. It's a very popular textbook. And I think the definition here is much more reasonable. So it's a loss of function strength. A loss of function strength based on your own application. It can be yield strength if you consider plastic deformation is not acceptable. It can be ultimate strength if you consider plastic deformation is fine for your application, right? And then the maximum strength in the maximum stress, the actual maximum stress in the structure. So they put it as allowable stress. It's a little bit confusing in terms of the name, but I think what it means is the actual stress, actual maximum stress in the structure. So I think this definition is much more reasonable than the definition in the two versions of mechanics materials. So just be careful when you read a textbook. Textbook is not always correct. Textbook, you can consider its opinion of the author, and it's not always correct. Just use your critical thinking. Right now, we already learned the normal stress, shear stress is equal to force of area, different force, different area. Yes, there's a linear relation between the force and stress. But when you go to more complicated, we learn the Voronoi stress, we learn different theory, and we have the combined, we have the tensile stress, we have transverse force, tensile force, transverse force, torque, bending moment, all applied in one structure. And when we calculate stress at a critical location, the stress is not always in a linear relation with the force. So that's why in the other version of the textbook, it say that if the load applied is linear related. But if you check the Shigley's textbook, it say that this is a much more accurate statement. Stress may not linearly vary with load. So using load as loss of function parameter is not acceptable for calculating safety factor. Back to what I said in the introduction part of this class, structure does not fail because of force, it fails because of stress. So now this is the definition, a screenshot from the Shigley's textbook, Mechanical Engineering Design. Now let's go to the FEA textbook. And you can see that the safety factor definition, what is the original? The max von Mises stress. Okay, the original put it here as a von Mises stress, of course, is a maximum stress. Right now, it's too much to explain what is von Mises stress, but I will talk about that later. It's basically we need for combined loading, we need find a stress that when it fail. We call that one as von Mises stress. So basically, this is you can consider in a simple situation, it's a maximum stress in the structure. This is the yield strength of material, and let's say for now, let's just use this one as maximum. Safety factor is defined as yield strength of the material and maximum stress in your structure. For sure, similar, right? So I show you this different version of explanation about safety factor from different textbook. I just want to tell you that how to understand it when you see the difference in when you read textbook, why there's some difference. And I also want to tell you that do not always believe the textbook. Textbook is just opinion of the author. It can be right, it can be wrong. Just use a critical thinking to try to understand if it makes sense or not. So this is safety factor about the definition of safety factor, and make sure that you understand it should be defined in terms of stress, not force. So right now, for the two most popular version of the mechanical material textbook, their definition, they are wrong. This is the first version. This is the one I listed in the syllabus. This is the most popular mechanical materials textbook. This definition is definitely wrong. This is also another version of mechanical material textbook. This definition is also wrong. The one is correct is mechanical engineering design textbook, but this is not a textbook for our class, so I do not recommend, like, you really need to buy this textbook for our mechanical material. This is more advanced class. And this is FEA textbook, and of course you don't need to buy FEA textbook for our class. The key thing here is that follow my lecture. Yes, it should be stress over stress. It should always be stress over stress, because the relation between stress and force is very complicated when you go to more complicated situation. It's not always linear relation. Any questions so far? Okay, so in terms of the equation, this one is very simple. It's stress over stress, right? Now let's check the example problem. We have the link AB is made of steel. Yield strength is given. We want to use safety factor 3.2. We're only considering the failure of the AB here. We need to find out the cross dimension, cross shared area of the AB. And we assume that they're adequately reinforced at P9 and B. We are saying this because we learn later that for stress concentration, if there's a fastening hole here, there's stress concentration here. But for right now, we don't know that part yet. So we only focus on the nominal stress caused to failure, not considering here. Assume that adequately reinforced at pin A and B, it will not fail at pin A and B. So how to calculate the cross-section area of AB? how to calculate cross-section area by AB? Anyone?
Finding stress and then using the formula to find the area.
So we need to find the stress in the AB, and then because we have safety factor here now, it's not simply just this stress is lower than this one. We need to make sure that this one, well, yield strength over the maximum stress in the AB should be greater or equal to safety factor 3.2. So you can satisfy 3.2, right? So, and of course, the cross-section area, the stress you calculate in AB is a function of cross-section area, so you can calculate the area. But the first step, we need to figure out what is the normal force, internal normal force in the AB section, right? How to find the internal normal force in the AB section. Well, stress in the AB should be equal to internal normal force over the cross-section area. So cross-section area is something we need to calculate later. But how to find the internal normal force in the AB section?
Free body diagram.
Yes, thank you. Do free body diagram, we have different ways. Let's say, should we do the entire section, sorry, entire structure, or this part, or this part? Which one?
Should we do a free body diagram of BE and then treat AB as like a two force member?
Yes, thank you. Thank you. So let's do free body diagram of B. So AB is two force member, so that one we can calculate the internal normal force in AB. So let's say we have AB. We don't know the direction. Let's assume it's in this direction, doesn't matter. If we get a negative value, it means in the opposite. So let's say this is the force applied by the AB link to the pin joint B, to the joint B. To find FAB, do we need to write all three equations, or is there a way to simplify?
Moment at D.
Yes, thank you. Thank you. You can write three equations: force in the X, force in the Y, and a moment about a certain point. You can solve for FAB, you can solve for dx, dy, the two reaction force at pin joint D. But here, just realize that to find the cross-section area AB, we only need FAB. We don't need the reaction force at point D. So make sure that in your quiz and exam to save some time. Do not waste time on the unnecessary information. You only need one equation, that is moment about D. You can solve for FAB. You don't need three equations. So moment about D equal to 0. The X component FAB, of course, it passed through this point D, does not generate any moment. The Y component, it will generate the moment. Let's put the angle here. So this one is 35 degrees. So the Y component of the force AB becomes FAB times sine 35. And of course, this Y component will generate a clockwise moment about point D. So let's put a negative sign. What is the moment arm?
3.2. Oh, 4.2.
What?
Sorry, 2.8 from point D.
Yeah, 2.8, 2.8. Yeah. So Y component, this is the moment arm, 2.8. The next one is, of course, this force. This force will generate a counterclockwise, so it's positive. Change to pound and, well, feet doesn't matter because dimension is the same. It's all in feet, so. Since this is pound, so the kips I change to 5,000 pound. And the moment arm, of course, 1.4. How to calculate the moment generated by this part?
You find the equivalent force by multiplying 600 towards the base,
Yes. Okay.
and then it's at a distance halfway between the total base. So it would be at well, I haven't done the math yet, but it would be at 2.1 on the base. So however far that is from B.
0.7, right?
Yeah.
Yes. So yes, thank you. So again, the equivalent concentrated force is applied in this way. So it will generate a counterclockwise. So again, it's positive moment. And equivalent force is equal to the area under this one. So it is 600 times 1.4 times 3. And the moment arm, since this is should be applied at the middle point, so this is half of the 1.4.7. And so we can write this one as 600, 1.4 times 3. This is the equivalent concentrated force, moment arm, 0.7. And that's it, right? We don't have anything else. We are taking the moment about point D. So let's say force, moment arm, moment arm, moment arm. So we can solve for FAB. This is the first step. Second step, do we need to convert the? Yes, I already did because this is the 5 kips. I use 5,000 here. Right. This is already 600, so I use 600. For the feet to inch, well, since all this moment on dimension, they are the same, so it doesn't matter. Second one, we need to calculate the maximum stress that should exist in the structure. Based on our definition of safety factor, so it should be yield strength of a safety factor. Yield strength of the material is 65 KSI. Let's convert to PSI. Safety factor 3.2. Now we have pound, we have PSI. The dimension we get will be inch. Area should be inch square. So third step, calculate the cross-section area. We already know that the maximum stress in the structure is equal to FAB divided by cross-section area of AB. And this is equal to 5,457 pound area equal to PSI and area inch square. Any question? this is purely from statics. If you still confused about any static textbook content, please you can read the textbook, and if you have any question, we can discuss in office or in detail. So this one is very important at the beginning of the semester, because I mean, if you mess up this step, you basically mess up everything, right? Almost all of mechanical problem, the first step is always statics. Any question for this example problem specifically?
Can you explain what you did in step 3 again?
This one.
Yes.
So the maximum stress is equal to the internal normal force. Here should be the FAB we calculate in the first step, right? Divided by the cross-section area. Right. And this one should be equal to the one we calculate based on the safety factor. That's how we calculate area.
Okay. Thank you.
Welcome. Any other question? PSI and inch. Okay. So let me go back to the, oh, it's in a different lecture. So let me write here. PSI equal to pound per inch square. Right. Let's do one by one. So for the first question, is this part clear? Did I answer your question? Explained. Okay. Second question, can you explain where the value of yield strength coming from? Value of yield strength coming from here. So let's say in most the real life problem, when you determine a structure is safe or not, you a lot of time you know what material you use, right? So once you know what material you use, you know for that material what is the yield strength. You can find it in the handbook. Let's say I give you any type of aluminum or stainless steel. You can find the yield strength of that material. So this yield strength information is normally a given information, as long as you know what material you use for the structure. How you got a distributed load function. So for the equivalent force of this one, this is uniform distributed force. So basically it's equal to this one, 600 pounds per feet times this one, 1.4 times 3 total length. So this is the area under this load curve, right? And it should be applied at the center of the B section because, well, it's uniform distributed. So it should apply to center. So now if this is center, it's also the middle point of CD. So now this becomes 0.7. That's why we have 0.7 here. Did I answer your question about how you got the distributed load function? Okay, you're welcome. What does assume adequately reinforce around the A and B? So we intentionally put this one here because in the, let's say if this is a project problem, you need to check, of course, if it fail, it will fail or save here. But a place that's more likely to fail, if it's a real life problem and if it is a project, you also need to check at this link, because as this two pin joint, because as this two pin joint, you have a fastener hole here, and whenever you drill a fastener hole in a structure, it will cause the stress concentration, and that fastener hole may increase the stress level to 3 times more than the normal stress generated here. So in real situation, it may fail here and here first before it fail here. That's why for this specific example problem, I put the assumption here that it's adequately reinforced around pin A and pin B. It means that you can ignore the stress concentration here and here. You only focus on it if it will fail in between or not. Did I answer your question? Okay, great. So any other question?
I have one that might be related to that with the homework.
Yes.
That's the same reason why for tensile forces, you subtract the diameters of the pinhole from a link.
Yeah. This one, right?
Yeah, because I was confused on for compressive forces, why we just use the area of the link, but for tensile, we had to subtract the diameters.
Great question. So you probably already read textbook. The textbook just did the calculation like it's directed without much explanation. So let me explain in detail. We have 10 minutes. I think it should be enough. So for the tensile, you should imagine that if there's a tensile, the tensile should be in the BD section, in the BD link. When it's in tensile, do you agree with me that the contacting surface should be the upper side between the fastener and the inside half cylinder of the plate should be the upper part when it's in tensile, the contact surface,
Yes.
contact area, right? So in that situation, I have the drawing is not perfect, but you know what I mean. So this is tensile situation, and this is the contacting area. It should be in these two area. Let's focus on this fastener hole first. It should be in this upper half. So basically mean that, okay, now when you have tensile force applied, the force is fully applied in this whole part. And when we need to decide when the maximum stress equal to force over area, and if force is constantly in this whole section, we just need to find the minimum area. Where is the minimum area? It's not here. It's area that minus this empty part for the plate. Make sense or not?
You're saying to find the largest stress, it needs to be the minimum area because the area is in the denominator?
Yes, because normal stress equal to normal force over the area. Agree with me?
Yeah.
And since our contacting surface is on the upper part, which means that in this whole green area, it have the same normal force. It has same normal force. Make sense or not? Starting from here to here in the same. So this part is consistent. So now we want to find the maximum normal stress. We need to find wherever it has the minimum area. Where is the minimum area in this whole section? It's here. Because this empty part, you need to remove this empty part. This is a fastener hole for the plate. So that's why for the maximum stress, when there's a tension, we should use minus this diameter of the fastener hole times the thickness.
And that also, is that the reason why you subtract just the diameter? Because essentially you're subtracting 2 radii?
Yes, you need to subtracting this part.
Okay.
Yeah, makes sense or not?
Yeah, it makes sense. Thank you.
Okay, this is for tension. You're welcome. This is for tension. For compression, again, if you know that for tension, the contacting surface is this part, it's easy to understand it. For compression, this should be the contacting area for the fastener and the plate and the link, right? And if this is a contacting area, then the total force applied is gradually increased from the AA prime to BB prime. it doesn't matter. Let's put PB prime here. Let's say the total normal force is N. Internal normal force is compression, but it doesn't matter. And this N is not really 100% applied at this cross section. It's not, because this is a starting point of the contacting area. And maybe there is some positive force, but it's not definitely not 100%. It's gradually increase, gradually increase, gradually increase, gradually increase, and increase to this bottom point of this fastener hole is 100% normal force. Right? So for this situation, even though, okay, you say this is the minimum area, but for the force here is almost close to zero here, because this is starting point where the force applied. This starting point when you start contact. So the 100% normal force applied is starting from here, the bottom point of the fastener hole. And now it's really between the 100% force is only between BB prime to the symmetric part at the bottom. So now, if you want to calculate maximum stress in compression, you need to consider this is the maximum force. In this area, the force is gradually increasing. And how it increases is very complicated. We don't need to figure out. We know that the force, the internal force from A prime to BB prime is gradually increasing from 0 to 100%. How it increases? So far, based on what we learned so far, we don't know. But we know that it's 100%, it's maximum here. That's why when we calculate the normal stress caused by the compression, we need to use the entire cross-section area, which is this one. Does this make sense or not?
Yes, I understand now. Thank you.
You're welcome. Any question for this part? It's really truly understand. You just imagine you have a link, you have two holes, and you pull it. This should be the contacting surface. This should be the contacting surface between the fastener and the plate, the link. And if you push it, apply compressive force, this should be the contacting surface. This should be the contacting surface. So when your contacting surface is like this, at this point, is where the 100% of internal force applied. So now, in between this region to this region, we have the consistent 100% of internal normal force. So to find the maximum stress, we just need to figure out where the minimum area. Minimum area is located at here. You just need to minus this empty part, this fastener hole part. And for compression, this place has minimum area, but this place also has minimum force, right? It starts from 0 here, and it's really until this bottom part of the fastener hole, you have the 100% of internal force, compressive normal force applied. So this is a location that has 100 internal force, and so in the compressive situation, you need to use this one, the cross-section area. Yes, I will post a homework solution this afternoon. Any other question? Okay, if no question, we are done for the class today. I post a new homework. It's due on today. Today's, I don't know what day is today, but it's due before next class. Thank you for coming to class and have a great day. I will change the Zoom link
Thank
to the.
you.
You're welcome.
Thank you.
You're welcome. Have a great day.